happy, yes.
Start. Okay, it's my pleasure to introduce Dr. Mohammed Abdul-Mageed from University of British Columbia to give us this talk today. Mohammed is now an assistant professor of computational linguistics, information science, and computer science at the UBC, and a founding member of UBC's Center for Artificial Intelligence. His research focus is on deep representation learning and natural language sociopragmatics with the two main goals. The first one is development of a social machine for improved human health, safer social networking, and reduced information overload. And the second direction is the use of machine learning as a vehicle for making discovery with and about human knowledge. He completed a dual PhD degree in computational linguistics and information science from Indiana University in 2015. Before he joined the UBC, he also had multiple positions, including in Columbia University, Indiana University, and University of Pennsylvania. And Dr. Mohammed's lab has won several international shared task competitions, including in machine translation, dialectic identification, social meaning understanding, and effect detection. His most recent ACL 2021 work on Arabic NLP has been described as a milestone and improved over 2 decades of research. Some of the recent released model by Dr. Abdul-Mageed's lab has also been downloaded more than 15K times in a short period of 5 months. And his research has been funded over 7 million by places such as Google, National Science and Engineering Research Council of Canada, and Social Science and Humanity Research Council of Canada, and Canadian Foundation for Innovation. His lab is currently also supported by excess amount of computing resources from Amazon, A&D, and Compute Canada. So let's welcome Dr. Mohammed Abdul-Mageed today for his talk on deep learning for the social good. It's now yours, Mohammed. Thank you.
Thank you very much, Dr. Lee. I very much appreciate the kind invitation. I'm very happy to be with you today. And let me start by just checking if you can see my screen.
Yes. Okay,
great. And in case you see me like looking a little bit to the right-hand side, it's because I have another screen that I'm looking at. Okay, so as you can see, so this is the agenda. This is a title of the presentations of deep learning for social good. And I'm Mohammed, as Dr. Lee said, and I'm from UBC. The agenda of the talk will go like this. I'll talk a little bit about deep learning, and then I will talk about 3 main areas. I will talk about natural language understanding, and then I will talk about machine translation, and then speech. All right, so I usually like to start with a slide like this, where I talk about art and a few other related things. Also on the left-hand side, you can see this is from Greek mythology, because art has inspired AI in general, and people have always tried to imagine mythical figures and so on. So this is tightly related to AI. In the center, you see some sort of Islamic and Arabic art, which is also very beautiful. And if you do computer science, you know that the idea of recursion is important, and it's in nature, and it's also in art. Last thing here, I'm showing Ada Lovelace, because one of the things we're trying to do is to get like more women studying computer science. And this is a person who has done computer science very early on, and it should be an inspiration to many. All right, so that said, what we see here is on top left is the human cortex. And the idea here is that when humans understand, for example, through their vision system, this recognition of what we see doesn't really happen immediately. It actually happens at stages. So without getting into details, the idea is that we possibly can also try to build machines that recognize at stages. So more specifically in artificial neural networks, we will be able to build models that are layered, and each of these layers would help us identify an object to some extent until ultimately we are able to do the full recognition. And we call the network deep because it has several layers. All right, so you see also on the bottom left a convolutional neural network, which is basically a sliding window that convolves over an object such as an image and does some simple matrix operations. One of the classical architectures in deep learning, as many of you probably know. Also on the top right side, you see a recurrent neural network, which is basically a network that consumes the output from a previous time step. What you see here is actually a bidirectional recurrent neural network, and these have been very successful in doing things such as language processing, for example. ConvNets have been very successful classically in things like computer vision, although both these types have actually been used for everything. So ConvNets have been very successful in NLP, and also people have tried to use recurrent neural networks for image. What you see on the bottom right is basically the idea that you can take some part of a neural network and then put it with another part and then make it like work. So neural networks are simply said, they are like Legos. You can take one and then you can take another and then you can work with both of them. So the idea of an encoder decoder, for example, if you're trying to do machine translation, imagine taking an English sequence as input through a recurrent neural network as an encoder, and then trying to translate it into Arabic, let's say, through a decoder. And that encoder and decoder can be any type of neural network. It can be convoluted, it can be recurrent net, or anything else. Okay, then what happened is people invented the transformer, one of the most successful current neural network models. And it's basically based on the idea of attention. More specifically, the concept of self-attention. What you see here in the middle, this sentence, the animal didn't cross the street because it was too tired. The idea is that we take each token and we try to see how much of this token actually is connected to itself or to any other tokens in the same sequence. This is why we call it self-attention. So if you look at the bottom left side, so a token like it, for example, would be a query, and then we would be looking at each other token in the sequence and trying to see how much this token is related to any other token. And we work with this concept of key and value, and then everything will be in matrices, and then we will have lots of these matrices in different subspaces in order to be able to calculate this type of self-attention. This is meaningful. So for example, the example you see here, the word it refers back to the animal. So this is interesting and useful for some natural language processing tasks, such as what we call co-reference resolution. If you're translating, you want to be sure that the pronoun is actually resolved to its referent, which is the animal. On the right-hand side, you see something that is based on the transformer network, which is the BERT model. The BERT model is basically an encoder that's based on the transformer, and it's it looks complicated, but then basically you have some input, and then you get some encoding, embedding from this input through some sort of a concatenation of some regular embedding and then some positional embedding, not regular embedding, just some positional encoding, which is basically gonna give us this idea of sequentiality that is absent otherwise from this model. And then you pass this to a block of multi-head attention and some sort of normalization and addition and the feed-forward neural network. And then this also is connected to some similar block on the right-hand side. And ultimately, you have some linear layer, and you put a softmax, and then you can represent. So basically, this is very simply said the idea of the transformer. And BERT came out and revolutionized all natural language processing. However, it's only an encoder. So also people came out with the idea of an encoder and a decoder. And you can actually turn almost all natural language processing tasks, for example, into a text-to-text network. Basically, two networks, one that would take any sequence and encode it, and then one that would decode from there. So this can be used for machine translation, as I said, but it can also be used for something like sentiment analysis, where the encoder would look at a sentence and the decoder will try to say if it is positive or negative, for example. So this is a text-to-text transformer work that came out of Google. One thing that I'm not showing here is the generative pre-training model, otherwise known as GPT. Now there's GPT-3, as many of you know, which has also been very successful. It's an autoregressive language model that has been shown to be very useful for lots of tasks, especially tasks where you don't have a lot of labeled data. So it's very useful for what is known as few-shot learning. Okay, from there, what this is showing is that deep learning has had a very huge impact on natural language processing and also on other tasks. What I'm showing here is actually not very new. It's kind of 4 years old, maybe what's on the slide, but it has revolutionized machine translation, for example. In particular, not only classical deep learning neural networks, but also the idea of attention has been very, very influential. Came out around 2014, 2015, and it has caused a lot of progress. And then other ideas came out, of course, such as back translation, which is similar to self-training. Without getting into detail, so machine translation has been revolutionized. Speech has also been revolutionized. And then people also do what is known as image captioning. You can take an image and then ask the machine to give you a natural language description of the image, which is a confluence of computer vision and natural language processing, a very interesting field. Okay, that said, there are issues and challenges, and I'm focusing on 3 of these here. Basically, deep learning is really, really data hungry. So the most successful type of deep learning right now is basically supervised learning, where we do need huge amounts of labeled data in order to be able to perform a task. So this is a bottleneck, and so it's desirable to come up with automatic methods for alleviating this need. Another challenge is the idea of bias. So basically, a lot of data sets that are available for many tasks are created by humans, of course, and humans are either biased or maybe they are not fully aware of the full range of what should be done correctly or right or precisely and so on. And so there is bias in the data. And maybe the data doesn't cover all different communities or sectors of society. Maybe the data covers a certain race or gender and so on. And so the idea of bias is really important, and there is a lot of work going on to alleviate this bias and ultimately, hopefully, remove it. A third challenge that's also very, very serious is energy inefficiency. So in order to train a successful neural network, especially if it is a large one, you need a lot of GPUs, and GPUs use electricity, and then there is carbon emissions, and so on. So this is not really good for the environment. In fact, it's actually very harmful to the environment. So many of you may have heard about the GPT-3 model and how much energy it consumes, for example, to get trained. So people have said it's like five cars in their lifetime, the same amount of energy. Not sure if this is very strictly true, but there is some truth there. Okay. Now, this is the second part of the presentation. So I kind of try to move quickly so that I can get to tell you a little bit about some of the work we do in the lab. So I will talk about three main areas. I will first talk about natural language understanding and the examples of natural language understanding work we have been doing over the past 2-3 years. I will also talk about machine translation, and then I will talk about speech technology. So let's start with NLU, which is natural language understanding. I will talk about 4 things within this area. I will start with talking about dialects, and I will focus on Arabic dialects. Because Arabic is a language that has many dialects. Basically, when we say Arabic, what do we mean? Well, it's a collection of languages. It's not a single language. So you have what is known as modern standard Arabic, which is a modern variety of the language that we use in formal settings, in education, in some satellite channels that are pan-Arab channels, such as Al Jazeera or Al Arabiya, and these types of channels in many of their programs. There is also dialectal Arabic, and dialectal Arabic classically, people classified it into regions. So people would talk about North Africa as a region or the Gulf as a region, and so on. What I'm showing here is actually different countries rather than regions, because I think there is more nuance than just saying the Gulf or like North Africa. There is also actually, in addition to MSA, which is modern standard Arabic, and the dialectal Arabic, there is what is known as classical Arabic, which is the type of Arabic that was used in pre-Islamic history, in literature, in poems, and so on. And it's also used in a lot of literary and religious discourse even today. Okay, with that said, I'm looking here at some sort of what I call macro variation, which is, dialectal varieties at the level of the region, maybe a little bit at the level of the country. And some of our work was basically focused here, trying to collect the data and build the models that represent these different dialects. And what you see here on the top panel on the left-hand side, if I take a word like, for example, rajul or jada or luzum or basha, these are words that would translate into the word man in English, but they come from different dialects. And when we take each of them and try to cluster most related words to each of these, they would actually form like different clusters, as you can see here. And each of these clusters is basically one dialect, which means that based on the models we have built, we are able to represent dialects quite well, which we also show on the right-hand side on the top in this table. If I take, this is basically a word embedding model that you can get from a model such as Word2Vec, for example, if you feed it a lot of dialectal Arabic data. And we have built these models. So if I give it a word like izai, which is an Egyptian Arabic word, and I ask the model, give me similar words, it will give me lots of words that are also Egyptian, like kida, bardu, dilwaqti, alashan, and so on. Why is this useful? Where it's useful for the whole range of natural language processing work. So take the example of machine translation, as I show in the bottom part here. I take a sentence from Egyptian Arabic, such as الواحد مقريف وعاوز يضرب كوبايتين شاي في الخمسينة. If you know Arabic and if you know Egyptian, you will know that this is really highly dialectal, and it's really highly Egyptian Arabic. I gave this sentence to Google a couple years ago, and this is a translation Google came back with. Like, it's really not able to translate, the sentence very well. So, for example, the phrase "fil khamsina," it translated it in the 1950s, which is not really what is meant here. "Fil khamsina" just means like very high quality, very good tea. Okay, so these dialectal representations should actually be very useful for a task such as machine translation, but also across the board for many other tasks. Okay, hopefully I have convinced you that this is useful, and you can use different types of neural networks. I'm showing bidirectional LSTM network here on the bottom left-hand side. And then we go from there to this idea of, now that we've talked about macro variation, I'm talking about micro variation, which is, okay, can we take neural networks and do something even more difficult or more challenging, which is also meaning that it's more exciting. Can I get a neural network to predict the dialect of a city across the Arab world? And this is the work that we have presented last year in EMLP. Basically, we built models that are capable of predict, given a sequence of words like such as a tweet, they are capable to predict from which city, from all these cities, it is coming from. And basically, a lot of people don't really believe that, and many people even say, like, how come? How is this possible at all? And so on. Well, there's a lot of field work, theoretical linguistics field work. It's more focused on speech, but it actually shows that there is a lot of variation. Of course, when you go from speech to text, it's a little different, but there is still some signals there, and we have shown this. So you can go to the paper and take a look. But you can imagine why this type of model would be useful for many, many different tasks. For example, you can imagine this model being useful for disaster management. So assume somebody is, in a difficult situation, they are posting a tweet about a fire, let's say, and our ability to know that this tweet is coming from this particular place would help us to, put some energy there and help and alleviate the situation. Okay, we built different models. What I'm showing on the top left-hand side is actually this beautiful image of the coverage of the data we have collected. This is Morocco, and we have coverage of all these different cities and different provinces in Morocco. One thing that we do also is this idea of code switching. So different Arab countries, actually, when they speak in a non-Arabic language, they don't always switch to the same foreign languages. Some countries would switch to English, some countries would switch to French, or some other foreign languages. So we actually exploit this signal in the data as well, because there is a different distribution of code switching. So we exploit this in our models, and we show that it's actually a useful signal, as you see on the table on the bottom right-hand side. And of course, we build different types of models, hierarchical, multitask learning, and so on, which is also interesting and useful because there is some theory in neural networks that says that, okay, if you're trying to learn different tasks, if you have a task that's easier, maybe learn it first and then take this representation, learn a task that's much more challenging. So we also show that, this is possible here, and we sort of confirm some of this theory. Okay, what does a model learn really? Well, on the left-hand side here, I'm showing a tweet that's coming from a city in Egypt. It's called Asyut, and the model was able to predict that it is Asyut. And the CLS token here, which is coming from ARBERT model, is actually attending to tokens that are Asyut Arabic. It's like Upper Egyptian. It's the type of word that, if you know Upper Egyptian language, you know that people would say يخرب مطنك, غورت الرادل. Instead of saying الرجل or الراجل, they would say الرادل. So the model is actually attending to the right signal here. And on the right-hand side, even like the word غور is also, this token is also attending to things that would also cluster with the same token. So this is a concept of self-attention. So hopefully this is convincing. And here is actually something that is also convincing, as far as I can see. We take a tweet, for example, from the city of Marsa Matruh in Egypt, which you see like the black circle here, and the model actually makes a mistake. It doesn't correctly identify this tweet as coming from Marsa Matruh. It actually classifies it as coming from Tobruk in Libya. What is very interesting here is that actually even the errors of the model are meaningful. So the model could have all possibly classified this tweet as belonging to Alexandria, Egypt, or Al-Mansura, Egypt, or Cairo, Egypt. What it did is actually it assigned it to a nearby city, even though it's in a different country. So it crossed the border, yes, but it didn't travel for so long of a distance. Okay. I would be happy to take a question if I heard some sound, but if you have something that's really pressing, you can try to ask. I will try to answer, but I will also sometimes say, okay, let's put this off till the end. But yeah, I'm open to that.
In the previous slides about this transformer, you have some hash key added to some of this token. Yeah, for instance, this hash.
Right.
What is this for? Is to
Right. So this is so each token is actually represented as a subword segment. This is what is known as byte pair encoding. So it's a simple algorithm that would take a sequence of words, and it would take each word and it would split it into subcomponents that people refer to as byte pairs. So a great question, and sorry I failed to actually explain what this is, but this is just showing the borders between each byte pair and another.
Okay.
Yeah, and this is useful in that it actually alleviates what is known as data sparsity, which is like, if Arabic is a language of rich morphologies, meaning each token has a lot of grammatical information expressed at the level of the word. So a single word could have lots of gender information, person information, number information, and so on. And this makes it challenging from a machine learning perspective. Before neural networks were popular, a lot of people have, including me, have invested effort into trying to represent this morphological information to the models, such as the models can actually do well. And we basically were trying to alleviate this data sparsity issue. But with this algorithm of byte pair encoding, this actually alleviates this concern very much.
Right.
Okay. Yes, so now I'm moving to another area or theme, which is the theme of misinformation. We've done some work on English and multilingual, but also in Arabic within this area. What I'm showing here is a work that we just presented in European ACL 2021. And basically, when COVID came, we were trying to put some effort and energy in order to help. And what we were able to do is to collect a massive scale data set from so many different countries, so many different cities, and 100 plus languages that we showed to be useful in multiple ways that I will not talk about, but I will just mention that on the left-hand side here, for example, on the top, we were able to discover what is going on Twitter, in the sense that we know that people were tweeting much more than normal. So it's like, everybody was on Twitter and tweeting. In fact, if you look at the nuanced patterns of usage of the network, you will find that, and we tried to compare to previous years. So we have a longitudinal data set, and so you find that people actually were retweeting much more than they were directly tweeting. So you see the pattern in 2020, totally different from all previous years. So the pandemic really changed these established patterns of communication over the network. One other interesting thing that we see happening is that people were actually communicating with one another, so through what is known as replies, much more than they did in any previous year. So in fact, the replies are almost equal to the directed tweets, which is also another pattern that never happened before based on our data set. And it's large enough data set that we feel that these results are actually good and solid and so on. What you see on the bottom here is, so we built like different types of models, including misinformation detection models using some external data sets that we acquired. And we show that the models are actually capable of discovering misinformation from the data. So these two examples are examples that the model actually discovered. So these are predictions from the model. So Vatican confirms Pope Francis, and 2 aides test positive for coronavirus, for example. That's like a piece of fake news. Royal Palace confirms Queen Elizabeth tests positive for coronavirus, and then a URL. So these are things that the models discovered. And there are, so the top right-hand side here are two things, basically. So the one with the Twitter logo is basically, it's basically an article that I wrote in the Globe and Mail, which is a mainstream Canadian newspaper, about this work. So check it out if you have interest. And then I also wrote like a Medium post about this in very lay language. I thought that this is an important enough topic that maybe I should mobilize beyond the academia, and so I invested these efforts. Okay. Moving from COVID to actually some fake news detection work that we did, particularly in Arabic. What we do here is actually two things. First, we create machine manipulation models. So we take a sequence of naturally occurring language, and then we edit it very skillfully in order to change its factuality. So the example you see on the left-hand side here is talking about Mohamed Salah, which is an Egyptian soccer player, moving from one, place to another, like, one club to another, one sports club to another, for a certain amount of money. And we can say that he's moving from Leeds to Madrid or to Valencia or whatever. Like we can use like names of cities, for example, which are usually these sports clubs are named after, or we can edit the amount of money that he was paid to move from one place to another, which basically results in creating misinformation. And so we had a method to do that automatically, and we also created models to detect that automatically. And then why would that be useful? Because we showed also that we can take these machine manipulation models and we can use them to improve detection of misinformation and fake news. Let's say a piece of fake news about, I don't know, garlic curing COVID, for example. So without getting into details, we showed that this work can actually aid the actual misinformation detection. But on its own, machine manipulated text is dangerous, right? So it's a task on its own. Okay, so we have this thread of work on Arabic, and we actually just presented a paper in NACO this year. It's a workshop in NACO that is talking about also Arabic misinformation and stance detection and so on. I'm not showing it in this talk. Okay, now I'll move to another area, which is what I call sociopragmatics. And sociopragmatics is basically about teaching machines quote unquote social skills, so we would like to know how language functions in the context, where we want to know who said what to whom, when, why, how, and so on. All these questions are important questions. The same sequence can be uttered in a context and it will mean something, but in a different context, it will mean something different, and it's the same sequence. So language is really positional, it's really contextual, and the goal of these types of models that I will talk about is basically to try to capture some of these. So you can simply think about tasks such as sentiment analysis or emotion detection or humor detection or irony recognition and so on as models that are within this area of sociopragmatics. Okay, pragmatics is a subfield of linguistics that's basically about meaning in interaction, how meaning changes when people interact. It's a whole branch of linguistics. Okay, so now I'm just talking about a single work here, which is this tool which we created a year ago. We called it ARBERT, and it basically does a bunch of sociopragmatic tasks. So it's capable of detecting dialect, which I talked about, but also age, gender, emotion, irony, and sentiment. We released this tool, and we have shown that it's effective and so on. And what I'm showing actually on the right-hand side is an external work that was done by Conlon and Brenner. It's a 2020 work that actually took a bunch of tools that do sentiment analysis, including our tool, and they compared them. They were able to show that ARBERT, our tool, is actually much more effective than all other tools, including tools from Google and Amazon and Stanford. And so we were happy to see people using the tool and also doing these types of comparisons. Okay, now I will move to yet another area that falls within natural language understanding, so which is language models. Really, language models can fit into natural language understanding or natural language generation, things like getting a model to write language or do machine translation, for example, and so on. But I'm focusing on the role within natural language understanding here. Happy to take a question before I start. I feel like I've been talking for a while, but if there's any question, please feel free to interrupt me.
Yeah, all good.
Great. So this is work that I am super excited about. This is a 2020 ACL paper that we just put the camera-ready version of it on archive earlier this month, so like less than a week ago. And it's basically about two language models that we have created, ARBERT and MARBERT, that do Arabic natural language understanding across a cluster of tasks. And basically, we spent a lot of time tracing back every single data set that we could find, trying to standardize this data set for deep learning and trying to compare to every single state of the art that we could find. And we came up with the two models, but also with a new benchmark for Arabic language understanding evaluation, which we call ARLUE. And the models are publicly available. We put them on MARBERT, on Hugging Face. So ARBERT and MARBERT. And what, like, this number of downloads just blows my mind. Like, a day ago, it was 15,000 something. I think in a single day, it moved to like 800 downloads. So this just shows the impact of this work, and basically in general, the fact that natural language processing and deep learning is really, really hot right now. So it's a very important field. So if you're trying to do your graduate studies, just come and do this work with us. Okay, so let me quickly talk about the paper. So basically what you see on the top left-hand side is a table with data sets that we have used and to pre-train the language models, the number of vocabulary in each of them, and also the number of parameters in each of these models. Maybe an important thing that I would say here is that our ARBERT and MARBERT models are 163 million parameters compared to other models such as XLMR large, which is from Facebook, which is 550 million parameters. So it's basically 3.4 times larger than our model. And we will show that our model actually performs better. So this is the point that I mentioned in the beginning. We want to create models that are more energy efficient. So smaller models are by default more energy efficient. And so what you see on the bottom is basically a description of the benchmark that we created, ARLUE, and we cluster it into a number of tasks. So there is ARLUE Senti, which is sentiment analysis, ARLUE SM, which is social meaning, and I'll talk about social meaning in a second, ARLUE Topic, which is topic classification, and different types of dialect, binary dialect, which is MSA versus dialect, and region dialect, which is like Gulf versus North Africa and so on, and country level dialect, which is like each of 21 different countries in the Arab world. And then we also have named entity recognition, and then the last row is about question answering. And we actually show state-of-the-art performance on all of these tasks that I will show you in the next slide. On the top right-hand side, basically these are the data sets that fit inside ARLUE SM, which is social meaning. So I talked about ARANET. Here we actually do this work and we improve even over ARANET that I showed like a few slides ago. So age, dangerous speech, emotion, gender, hate, irony, offensive language, sarcasm. So these are the individual tasks within the social media. But inside each cluster of these tasks, we have several data sets. For example, sentiment analysis, as you see in the table on the bottom, we have 17 different data sets. So a huge amount of data and effort that we have actually exerted to do this. Okay. Now, this is just showing how much we do on this benchmark. So basically, we're comparing to models from Google, models from Facebook. So MBERT is from Google, XLMR, base and large are from Facebook. ARBERT is another Arabic-focused language model. And then the last three are basically our models. So ARBERT and MARBERT version 2. Basically, we found that our model was not doing well on question answering because the sequence length we trained it on was short. So what we did is actually we took MARBERT and then we further pre-trained it on longer sequence, and that's what we call version 2. And then that was successful on question answer. In any case, this benchmark is useful because it gives a single score across a different number of tasks to test how good a language model is. So we come up with this ARLUE score. So our models are doing 77.4 on ARLUE score on these different task clusters. Okay. One more thing, this is also work that we presented in European ACL this year. It's work on also language models, but it's on self-training language models. We can take a language model such as that one coming from Facebook, for example, which is XLMR, and we can self-train it. Self-training is just basically you train a model, you fine-tune the model on some labeled data, and then you run it on unlabeled data, and then you use your own predictions under certain conditions to improve the model in the next iteration. Without getting into details, we just show that if we don't have models for dialectal Arabic, so let's say Gulf Arabic or Moroccan Arabic, we don't have models for part of a speech tagging or named entity recognition. We can take models that are trained on standard Arabic and then get some unlabeled data from dialects and self-train the models, and this is actually useful. So the table I show on the right-hand side shows you a word like nabi. It's actually not nabi, it's nibbi. So nibbi ni'raf min, like, which is like we want to know who. If this was a standard Arabic, it would be pronounced as nabi, which means prophet, but dialectally, it's actually pronounced in a different way, nibbi, but they are written in the same way. So this would confuse a model that's trained on standard language, not dialectal language. And we show that, you know, this process of self-training the model enables it to know that this is not actually a person. So this is the last row. The model that's not self-trained identifies it as a person, but our models identify it as a non-named entity. It's not a name of a person or like something that is used to refer to someone. Okay, so this work is useful for what is known as zero-shot and few-shot learning, which is, okay, you want to get a model to do well on a task without having sufficient labeled data for that particular task. So that's like few-shot, or without having any data for that particular task, which is zero-shot. Okay, you have to take this with a little bit of a grain of salt, because we are using still like MSA data. So it's not, you know, in the traditional sense of zero-shot, but it is to some extent within this neighborhood. Okay, so that ends my discussion about language models, and then I will start talking about machine translation. So machine translation, we've done some work on machine translation, different types of things, and machine translation is a very important task. And the reason is that it allows people to connect to one another. So we don't have to speak the same language in order to be able to communicate. When I was in Costa Rica like a year and a half ago, last thing I did before COVID, I remember a discussion that I have with a taxi driver, and this discussion only happened through his iPhone. And it's because of like machine translation models that we were able to talk. He doesn't speak English, I don't speak his language, and that was interesting. So machine translation is very important. And it's also a very challenging task. So what I show here is, on the top left-hand side, this is about Facebook's work a couple years ago in EMNLP, where they did some back translation, and they were able to get models that work very, very well. And they won the Best Paper Award. But then there's also, even though we have success, what you see on the right-hand side, it's me again messing with Google Translate, like putting some sentences. And I was able to show that when I add one more dot, look at the last example in the Arabic. I add one more dot to the end of the example, and the meaning of the sentence changes from the boy is a lion to the boy is a loser. Mm-hmm. It's because of the dot, and I'm not making this up. I actually did this. I took a screenshot of what I did, and this just like shows you that these models can be a little brittle, and so you get an article such as what I show on the left bottom here, the shallowness of Google Translate. This is Douglas Hofstede, a very interesting article that was written like in 2018. It kind of like criticizes the machine translation in general and so on. I suggest people read it if they are interested in technology in general. Of course, the state of the art is different now. So Google is better. Maybe everybody is better. So yeah. But that motivates machine translation. We've done some work on machine translation in different ways. Some of our work was basically taking some ideas, normalizing flows that's coming from some statistical work and machine learning oriented work that we show that we can actually exploit a little bit within the context of machine translation in order to improve the process. Although in this work, we didn't really get a lot of gain. We just get a little bit of gain, but this work was picked up, for example, by people in Apple and they sort of like improved over it and so on. So basically the idea here is that when you translate, you have an encoder and a decoder, and the decoder is basically an autoregressive model. It's a generative model. And because it's a generative model, it kind of samples from a distribution. And there's this idea of beam search, which is like at each time step you're trying to pick a sentence, you don't have to consider all the possibilities, because that would be expensive. So maybe consider the top N. And so there's a distribution that you are sampling from. And if you assume this distribution is a Gaussian distribution, this is probably not a very good assumption all of the time because of several reasons. So for example, think about this idea of word frequency in natural language obeying the Zipf law. So the idea is that there are too many words that occur very infrequently. So it's not really a Gaussian distribution. It could be some other type of distribution. So the idea here is that we assume there is a latent variable Z that we use in order to model. And basically, we try to kind of make it work by a little bit more tricks here and there, and using these normal flows, different types of normalizing flows, which are basically very simple functions that you can call recursively to change the distribution of the data and then sample from this data. Okay, so that was one thing. And then we also do work on low resource machine translation. Basically, I'm very interested in low resource machine translation because it's interesting from a machine learning perspective. How do we actually do well with small amounts of data? And we've been doing this on several languages. For example, what you see on the left-hand side is work on the African language Yoruba. And we're also starting to look at other African languages. And what you see on the right-hand side is work on a number of indigenous languages of South America. And yes, we don't have a lot of data. It's actually very small amounts of data. And the idea is that, can we transfer knowledge from high resource pairs to low resource pairs? And people have shown that this is possible. And we're also trying to explore different directions to do low resource machine translation in general. We also have some work that we have done that is useful for educational purposes, for example. So this is data from Rosetta Stone. So where it's a language learning app. So different people from different backgrounds, from different age groups would be able to translate differently. And if you want to evaluate these people, how would you do that? You can't really evaluate them in the same way. So we had a simple solution here, which is like basically try different models and take different models at different stages of the training process to match different skill sets of humans. Okay, I think I'm almost running out of time. I have a few more slides. How many more minutes do I have? If I may ask.
You can pick up 5 minutes.
Okay, great. So this is work that we did on translating from modern standard Arabic and Egyptian Arabic. So MSAEA means standard Arabic mixed with Egyptian Arabic on the one hand into English. And because there is not enough data for this code switched phenomena, then how do we do this? Okay, so it's kind of a hard problem. What I'm showing on the top left here is an example that says أنا عايز شغل جامد يا جدعان or يا جدعان. So if you give this to a human, the human will say, I want hard work, guys. If you give it to Google, then Google will say, I want a rigid job, جدعان, which is basically wrong translation. So Google doesn't know how to translate Egyptian Arabic. And basically, we train different types of models in different ways. Basically, we take modern standard Arabic machine translation data, we train a base model, and then there are some data sets for different dialects, including a little bit for Egyptian, and we kind of further fine tune different types of multilingual models, vanilla transformers, end-to-end, and so on. And we show that we're able to do reasonably well. And we actually won this competition. It was a competition in NAPL, a very recent one. And the system, the system output is reasonable. So actually multilingual language models such as MT5, which we trained on a small amount of data, is able to translate a word like فين, which is the last word in this example. مش عارفين نتأكد ومش عارفين البنات فين. This is the panel in the bottom here. So the MT5 is able to get it. The transformer model trained on 55 million pairs is not able to get it, but the language model is, even though it's only trained on 1 million pairs. Okay, and then we also do some work on English to a mixed English and Hindi. So I'm not actually going to talk about this for time, but we also do work beyond Arabic machine translation. This is involving other languages here. We came up with a very interesting method to do this, and our method we call it code switching from distributed representations. And as you see on the bottom right-hand side, we get like 12 point something, and we actually also won this competition. This was also in NACL, and we're presenting this paper, I think, in 1 or 2 days. Okay, so that said, I move to the last area, which is speech. So we have been doing some work related to speech, not too much energy in my lab directed to speech, but we are actually working much more on speech right now. I have two graduate students and a postdoc focusing on this this summer. So, but we have done some work in the past. So, for example, this work is taking a grapheme, which is a written orthographic form, and then changing it into a phoneme, which is the representation that you will use in order to pronounce. So the table on the left-hand side is showing this across a number of languages which have different types of alphabets and alpha syllabary and syllabary and so on. A little bit more linguistic knowledge involved here, but we take a source orthography and then we translate it into what is known as IPA, which is the International Phonetic Alphabet. If you have the IPA sequence of a word, that means you can pronounce this word. So this is basically text to speech. So we did this on a multilingual fashion. So we created a single model that would take these graphemes and convert them into phonemes across these different languages. We also built like individual models for each pair and so on. But I'm showing, I'm showing only one table here. Okay, this is actually my last slide before I go to just thanking people and so on. This is focused on imagined speech recognition, which is basically the task of, okay, you get somebody looking at the screen and you show them some words on the screen. You ask them not to speak, but just think about the word they are seeing. And then there is some brain activity that takes place. You record this brain activity through what is known as EEG. And then the task is now to try to decode, to tell what the person was thinking about. Which word did the person see on the screen and think about it without pronouncing it? This is called active speech, like imagined speech that's just happening in the brain, okay? And we published a couple of papers, one in ICAST and one in Interspeech about this work. This work is getting noticed and many people are starting to cite it. And basically we had, I mean, I don't have time to talk about details, but the EEG signal is really complex and noisy. And we were able to take it and put it through a number of steps that actually enhance it, squeeze something out of it, and so on, including very complex types of neural networks, such as a regular convolutional neural network, a temporal convolutional neural network, a deep autoencoder model, and then some other. We do what is known as intermediate classification. So I had this idea of I don't want to predict the word right away. I want to first tell if this word has a sound that's like a consonant or a vowel, just as an intermediate step. And then I would take this knowledge and pass it to the next step, which is trying to decode which word the person was thinking about. I mean, we only had a few words here, like I think 11 words or 13 words. I don't remember very well, but so this is a toy data set. But when you think about what we're trying to do, it's not a toy data set at all, because we're just like decoding from like what people think. So anyways, so this is work that is interesting, and it could be picked up, and people could enhance it and so on. I would like to thank all my collaborators over the years. I mean, many of these people are in my lab right now. Some of them are people I have worked with in the past and so on. So they have been excellent, and I've learned a lot from everybody, including my own students. And then I would like also to thank all the funders that have given us money to be able to do our research. So our current research is funded by a number of Canadian organizations, like the Natural Sciences and Engineering Research Council of Canada, the Social Sciences and Engineering Research Council of Canada, and then many others, like Canadian Foundation for Innovation. And we have a number of cloud computing resources that we're very grateful for. With that said, I would really like to thank you so very much, and I appreciate you taking the time and being with me to be in this talk.
Thank you very much for the talk. There are already some questions coming out, at least I can see in the chat. One question is, you showed several different variants of this BERT model. They, I mean, good for all the tasks, or specific model is better for specific downstream task?
Yeah, great question. So, you can classify models in different ways. So BERT and models similar to BERT are basically encoders. So they are good for natural language understanding tasks, such as sentiment analysis and any text classification task, for example, such as emotion or dialect ID or question answering. Actually, question answering can also be done with like encoder decoder. So BERT is an encoder only. The T5 model is an encoder decoder, so it has like these two, and so it can be used for things such as machine translation, so input output, question answering, input output, and so on. However, people have also used BERT-like models for you can build a network that's like sequence to sequence, like input output, encoder decoder, and instead of starting it from scratch, you start with weights learned through BERT. So in that way, you can kind of like use it in an encoder decoder setting. There are also like these autoregressive models such as GPT-2 and 3 and so on that people have used for many natural language understanding tasks, but they also write language and so on, so they can be used for generation. I don't know if the question is talking about the Arabic ones that I have showed, or just like the different families of models in general. But if you want to work with something in Arabic, just go and use our BERT model that we call MARBERT. It's the state of the art right now, and as I have shown, it's performing really, really well.
Right. So I have a question about the BERT model or MARBERT. So there's many, in some sense, prior knowledge and grammatical or other knowledge about the language, for instance, Arabic language. How would one incorporate some of these knowledge into the transformer-like model instead of using lots of data trying to learn that back again, right? What is your thoughts and comment on this?
Right. So there is a lot of work, as you might be aware, that tries to incorporate like knowledge BCs, for example, into language models. So people have used knowledge acquired from Wikipedia or like DBpedia or any other knowledge base to enhance these language models. For example, you know, if I have a named entity, like a name of a person, and you know, BERT would give me some sort of an embedding for that named entity, I can go to the knowledge base and then retrieve all the connections, like this named entity is connected to this company or this other person and so on, and then integrate this knowledge into the language model so that the language model can actually do better. So it would have like this added benefit of a knowledge base. And there are, you know, other ways to incorporate different types of knowledge into these languages. It's a very, very active area of research.
I see. So actually, the other direction is, suppose BERT has been pre-trained with lots of text. How would one, for instance, extract some knowledge from BERT, like, or understand what kind of knowledge has been learned or encoded in BERT? What do you think about this?
Right, so people build whole lots of diagnostic tests to kind of see how good a language model is. So for example, if I wanted to, and this is also related to issues of bias and so on, right? So if I wanted to know what type of knowledge BERT have learned about a certain racial group or a certain, you know, a person, for example, or a certain company, I could get BERT to give me the most similar words to that like named entity or the name of that racial group, for example, and so on. And you know, if it gives me lots of like negative connotations and so on, then it has learned something that's very, very negative. And so the answer to the question is that, you know, people build these. I don't work on these diagnostic kind of types of tests and so on, but I'm aware of them, and I have a PhD student who has done a little bit of this work in the past. I mean, they also learn like, you know, different types of knowledge such as syntax, semantics, and so on. So people come up with different types of levels of language, like tests that are based on different levels of language and so on. I think I had something in mind about your first question about the language models and how would you, there is some work that, so this is not exactly your question, but you know, if you have trained a language model on a certain language, but now you want to use it for a different language, right? Okay. So, and the problem is that, you know, it doesn't have the vocabulary from this like new language. So people are trying to rehabilitate, I call it rehabilitation, these language models by kind of like starting to like build a new embedding layer and so on. And there is some success in doing that. Like people have shown that, you know, you can take the representation from English, for example, and start with it and try to teach the language, you know, like the model, a different vocabulary from a different language. Now, of course, success is kind of depends on the language family, like, or do these two languages share the same orthography? Like like if both of if it is like English and French, well, yeah, I mean, like very similar. But if it is like English and Arabic, which is like even a different script, then there's a big gap between these two. So there's a lot of work that's going on around, you know, like making use of language models beyond what they were initially built for. So that's also a very interesting direction. We have some work, you know, it's still like in early stages.
I see, great. Any other question from the audience? So actually I have one final question. So for instance, if someone wants to improve the BERT model, transform model for Arabic language, is there any need for instance, designing new architectures or, you know, building the model differently or pre-train it differently in order to, you know, get better performance for Arabic language?
You mean training it from scratch or further pre-training it?
Yeah, scratch, and then maybe you need a slightly different architecture comparing to the current one. And is there any need, or because the Arabic language is so different from English, right? And maybe there's some places where a different deep learning architecture would be more helpful.
I would have a hard time justifying a different deep learning architecture that would be focused specifically on Arabic, simply because I think the transformer model is kind of a general purpose, and I don't think it's a good idea to try to, for each single language or like even like group of languages, to come up with something that's kind of different, because I don't see how it would be different. I think a general model, like a general architecture, is useful because it's like much more widely applicable and so on. However, with that said, of course, you would have to bear in mind the nuances of the language. So Arabic, for example, is a very morphologically complex language. So when people started training these language models, so before we started doing this, people would take the running text and then would actually use a tokenizer. In Arabic NLP, we call it like segmenter and so on, not exactly a tokenizer, because there are differences between the English morphology and the Arabic morphology and so on. And so they would split off like the word into its tokens and so on, and then they would train the language model based on like feeding it these tokenized text. However, when we did that, we didn't feel like there is a need for this, even though I have, when I was a PhD student, I have already created a segmenter that does very well, so I could have possibly used it. However, when you pass the text through this byte pair encoding very simple algorithm, it will split it off into these like byte pair small subword components that will alleviate all the concern of data sparsity that comes with Arabic. So a lot of people, when they talk about Arabic, they keep talking about rich morphology, complex morphology, and so on. And I get that, and I know it, and I've worked with that, for a long time. But I don't right now, I don't really see, that being a big of a deal if you have a ton of data. If you have a lot of data, and if you use like this byte pair encoding algorithm, or like, some other models use like another like sentence piece, they call it sentence piece. Then that would solve a lot of these issues. The other issues that exist there is that most of the existing data is really not representative of the different variation that exists. So if you want to represent like Moroccan Arabic, do you have data from Moroccan Arabic? How would you get data from Moroccan Arabic and so on? So I wouldn't think architecture-wise, I would think data-wise. And that would impact, and we have already shown that with our MARBERT model.
Okay, great. Thank you very much, Mohammed, for the nice talk. And then we can rest for maybe 5 minutes or so, and you can meet with other faculty, and they might have other questions, right? They differ.
Absolutely, yes. And I understand I'll go to the Teams.
Yeah, that's right. Yeah.
Okay, great.
Great. See you soon. Bye.
I'll be back. Yeah. Thank you.